In this video, we will talk about how to find the direction of magnetic fields produced by different types of magnets. In this slide, we are looking at, in the picture, we can see the Earth shown as a sphere, and we're going to discuss about the magnetic field produced by the Earth. As it is written here, the Earth's core acts like a very large magnet with its magnetic south pole near the geographic north pole. This is very important. The south pole of the magnet of the Earth is located at the geographic north. And this is the reason why the magnetic north pole of a compass always points towards the Earth's geographic north, which is actually the Earth's magnetic south. So in the end, the Earth's magnetic pole that is near the geographic north pole is actually a south magnetic pole, and this is an important point. The geographic north pole is actually a south magnetic pole for the Earth. Now, having known that Earth produces magnetic field, permanent magnets produce Earth field, and current wires produce Earth field, now we're going to talk about how to find the direction of the magnetic fields produced by currents. And in this picture here on top, we are using something called the right hand rule type 1 or the right hand thumb rule to find the direction of magnetic field lines around a straight current carrying wire. And so in the top picture you can see that the current is pointing upward, shown by the blue arrow here, and that's where the wire is shown in the brown color. And so to find out the direction of the magnetic field around the wire, what we'll do is we'll point our right hand thumb in the direction of the current. That's the first step we need to do. And then we'll pretend as if we are holding this wire using our right hand, and we will look at the direction of the curling fingers. And we see that so the important point here is that the thumb should be pointing in the direction of current, and when we observe the direction of the curling fingers, they give you the direction of the field. So that direction of the tip of the curling fingers at any point in space gives us the direction of the magnetic field at that point. That's important, and we will see several examples of using this right hand thumb rule, sometimes also referred to as the right hand grip rule. This is the example again shown here. A straight wire going up using the right hand. Importantly, we need to use the right hand, and imagine that we are holding this wire such that the thumb points in the direction of current, and then we observe the direction of the curling fingers at different points in space, and the direction of the curling fingers gives us the direction of the magnetic field at any point around the straight current carrying wire. In this example, we are using the right hand rule 1 or the right hand thumb rule or the right hand grip rule to find the direction of magnetic field around a current loop. And in this example, the current loop is shown in white color, and the white arrows show the direction of the current in the loop. And as we can see, the current is flowing in the counterclockwise direction. Again, following the three bulleted points, pretend as if you're holding this wire such that the thumb is pointing in the direction of current. This is the direction of thumb, and that's the direction of current. We do that, and then the red color circles give us the direction of the field, and we can see that the field is making circles around the coil or along the loop. Important point to note here is that the magnetic field points outward in the region inside the loop. So here it's pointing outward. And all the curling fingers point inward in the regions outside the loop. And we can see that here, in all these regions, the field outside the loop is pointing outward. In this slide, we are using the right hand rule to find the direction of magnetic field around a solenoid. So we are defining what a solenoid is first. Solenoid is a long coil of wire that has the same current I passing through each loop. So here we are seeing a battery or a voltage source providing current in this direction, and as the current flows through, it is going through the coil, going up like this, and then it comes back like that, and then goes on from positive of the terminal to the negative. And by using the right hand rule, if you were to hold any single coil, for example this coil, the current goes up. And if the thumb is pointing upward, the curling fingers will point into the solenoid. This is the field direction. So you can see that the field goes in, and if you were to hold this section, you will see that the field goes out like that. This is the field, and these are the currents that we shown earlier. And because of this property of the fields, we see that the field is going into the solenoid like this, going all the way, coming out. So that's the direction of the field, and we will see that the field happens to be parallel to each other. That means the direction of the field is same, and it so happens that the value is also same. So that's why a solenoid is useful instrument, because it generates a uniform field inside it. And it has several applications. For example, in MRI diagnosis or imaging, a solenoid is used to create magnetic field, which needs to be very stable. Now here in the bottom picture B, I'm showing you a cut version of the solenoid shown in picture A. You can see that the current is shown by crosses on the top wires or top sections of the loop, because the current is going in from the top, and we can see that at the bottom the current is pointing outward. So this is pointing outward from the screen, and once this is essentially the same representation shown by the blue arrows here. And with the right hand rule, now we are denoting the field. We see that it's going in this direction, shown by the blue arrows. These are the field. So field, this one. So it acts like a magnet, that this is the south pole of the magnet, and this is the north pole of the magnet. So a solenoid essentially is acting like a magnet. If we send current like this, we see that this becomes the south pole and this becomes the north pole. Lastly here, this slide, we are using the right hand rule or the thumb rule to find the direction of the magnetic field around Earth. And we have seen the Earth is like a magnet, and the south pole of the magnet is located at the geographic north pole. We have seen that before, and now by using this assumption or the knowledge that Earth's core is a bar magnet. I'm showing you the field generated by the bar magnet, and we see that if you have a north pole on top here and the south pole at the bottom for the bar magnet, the field lines start off from north, they go all the way from north to south. This is how the field lines look like for a bar magnet. And because Earth is also a bar magnet at its core, we see the field lines shown like this here in the right image, which can also be verified by using a compass. This is the reason why the compass always points towards the magnetic south pole, which is the geographic north pole of Earth.